Up next, we have Kyle Banta talking about the bomb calorimeter.
Hello everyone, my name is Kyle Banta, and I'll be talking about the bomb calorimeter experiment, and I am the leader for Group 4. So a little introduction, the apparatus we'll be using is the PAR oxygen bomb calorimeter. It's designed to measure the actual heat output when burning solid and liquid fuel samples. It's used in a lot of labs and universities, so it's recently been accepted as the standard for accurately measuring heats of combustion. And while doing that, it also analyzes the actual products of combustion. So the goals for the experiment and the objectives for the students upon completion are fully understanding the apparatus that was used, the physical principles that go into the experiment and actually burning the fuel samples and seeing what the products are, the procedure itself that's step-by-step in the lab manual, and the analysis techniques both for recording data and calculating the thermal capacitance of the calorimeter and determining the gross heat combustion for the provided samples in the lab. So a little background and theory. The heat of combustion defined is the actual number of heat units released by a specific mass of a given substance when combined with oxygen in a confined space with a constant volume. So in the lab, we'll actually be measuring out a specific amount of fuel, putting it inside of the bomb, vacuuming out the air, and then igniting it. So once ignition has occurred, heat is then transferred from the actual surface of the bomb, since there's no more air in it, to the water that is surrounding it by means of heat conduction, and by observing the water temperature and the change that occurs, it's possible to calculate the heat units that were output by the ignition. So the basic equation that this lab is going to use is the first law of thermodynamics, Q equals mcv delta T, and you can also rearrange that equation. So if everything but the fuel itself is chosen as a thermodynamic system, the equation can actually be written as mcv of the calorimeter is equal to Q over delta T, and where Q stands as the heat of combustion, and mcv is thermal capacitance, and delta T is the change in temperature. So there's also the other case when we don't know the actual fuel we're burning. So in that case, you would set Q equal to mcv calorimeter delta T, and all of your actual variables stay the same, but the equation is only valid if the calorimeter capacitance itself remains constant. So there's actually two sets of this slide. The first slide is going to go over the system as a whole, and the next one is actually going to focus on the bomb itself. So for the system as a whole, we have the igniter, which actually sparks the bomb to go off. The stainless steel bomb itself, like I said, that'll be discussed in the next slide. The laptop with the digital converter will log all the data as the ignition happens. Analog to digital converter, the water bucket to hold the bomb, and the thermocouple and water stir. So the actual bomb, you can see it cut away. The bomb lid itself has a check valve and a pressure relief valve. Like I said, we have to release the air that's actually in it once you load the fuel in. And the electrode terminals for the ignition switch, the crucible to hold the fuel sample on its own, and the ignition wires as well. So the casing around it is the bomb housing, and then you have the locking ring, which will be tightened in lab to hand tightness. So for my prediction of the results, pretty simple. The more fuel you add, the more heat units you're going to get output, the hotter the water is going to be. And after ignition, the pressure and temperature will both increase significantly within the bomb. And as your time duration increases, the temperature of the water will also increase until reaching a maximum. So viewing the different areas that we could reach uncertainty in measurement, the first is you have to cut a length of